Yeah, I mean, you don't even need that. So you'll see that on the next slide, you can extend, you can do the same trick for deadlock freedom and extend it to starvation freedom. In fact, so you don't need the assumption that the preemptions. You don't need. So what he's saying is basically, all right. So imagine I have a lock-based program now, and I'm trying to prove something similar. Well, if the probability that a certain thread gets stopped in the middle of the critical section is really, really low, then I could sort of extend it by the same argument, right? Okay. So basically, actually, you don't exactly. I mean, that is a valid way to fix it for lock-free, lock-based programs, but it's not exactly needed. So you need. So basically, you know that eventually each operation will finish. So unless you get some version of the schedule which always fixes the thread, fixes some thread inside the critical section, then you'll be starvation free. Okay. All right. However, that sequence where some guy, I mean, basically some guy is always fixed inside the critical section, that happens with some constant probability, because basically. Because of randomness, that guy could be fixed in there, or he could not. He could just be executed for some more steps. So technically, yes. I mean, you don't need to assume that it is provided by the scheduler. So basically, anytime you have an extension where a guy is fixed inside the critical section, you can argue that there's an extension with similar probability where that guy is not inside the critical section. So then you do make progress even in this case. Yeah, under this, yes, starvation free. Yeah, yeah, because technically, so this is a very important distinction, right? Because if I take, I mean, if I can just crash a thread inside the critical section, then there's no recovering from that. You'd have to assume that every thread has to be scheduled eventually. Just the scheduler just decides not to schedule that guy ever again, right? You can if this stochasticity assumption holds uniformly, then you get it. So basically, if it holds for any process at any arbitrary point in time, then you'd get what you need. Yeah, yeah. All right. Yeah. 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 Yeah, we're gonna. This is yes, yes. So basically, the unfortunate bit of business is that this gets exponential in B and N, like number of threads and number of processes. So this is why this is kind of morally, it's sort of a good result to keep in mind, but practically this is not a very useful result, because the upper bound on the completion time might be extremely bad. So I mean, if I tell you that your every operation will finish by like 2 months from now, it really is. I mean, yeah, sure, they will finish, but in practice, it's as if it was running forever, right? Yeah. Any other question? I think there was another question. All right. So I'm glad that this result gave you some thought, because it sort of it does stimulate thought. So this is basically proving this a bit more formally is one of your first assignment. So basically, all right. So this says that under any stochastic schedule, bounded log-free algorithms become weight-free with probability 1. So basically, I'm not sure if Nir showed you this on during his class, but basically him and Maurice have this kind of separation of progress conditions based on like basically minimal progress, where like stuff like deadlock free and lock free, which say under some assumptions on the schedule, someone has to make progress. So that's kind of minimal progress, right? And there are these kind of nice maximal progress guarantees, which say everyone makes progress. So there's starvation freedom in the lock-free case, where you assume, in lock-based case, where you assume that everyone has to be scheduled fairly by the scheduler, and then this comes to weight freedom in the maximal in the sort of arbitrary scheduler case. So the way you can read this is basically assuming with assumptions on the scheduler, you just look at this makes no assumption. This line makes no assumption on the scheduler. This line makes the assumption that no one gets crashed in the critical section. Okay, and then if you look at this, if you look at basically what this assumption, what this sort of simple theorem says, is that under stochastic schedulers, everything that guarantees minimal progress will essentially go to maximal progress. Actually, now I remember. So the question I had was yours. So basically, what lock-free algorithms do give you, and this is an area that we haven't. I mean, why are lock-free algorithms better than obstruction-free ones? Because they have more executions in which this guy who's, I mean, in which progress occurs. So there are more interleavings under which someone succeeds, rather than the single interleaving which you have for obstruction freedom, right? So for obstruction freedom, all I know is that if one guy gets scheduled, so practically there are only n extensions in which one guy makes progress. What usually happens in lock-free algorithms is that you have a lot of extensions under which progress is made. So basically this increases your probability of making progress globally. Okay, so does it make sense? All right, cool. So, and at the same time, this kind of gives some kind of theoretical muscle to these graphs, right? Because and now it sort of makes sense that there's this kind of random variable-like behavior where you show up, you try your operation, well, you don't succeed this time, next time you're just going to just try again and again, right? So, but eventually you get there, right? Okay. However, there are limitations to this, right? So practically, as your colleague noted, this is not that insightful, right? Because if I tell you that your operation is finished by next Friday, it really doesn't tell you much. I mean, maybe you go home happy, but you still have to wait until Friday, right? So the probability that a certain operation succeeds could be as low as 1 over n to the n, for instance. So this is not great. The other thing is, I really have to stress this. This does not give you sort of free rein to implement any lock-free algorithm out there and like sell it as weight-free to people. So there are real systems on which this will not work because the stochastic scheduling assumption does not work. So basically, if you look at NUMA systems and if you look at how memory accesses are scheduled, technically if you pin a thread on a faraway NUMA node and you have a lot of threads on another node, basically that thread will essentially, the length of its quantum, basically every time he gets the access to the data, he only gets it for a single step. And then all of these other guys will essentially, so you get scheduled at a step, then the memory gets taken away from you. You get scheduled at a step, memory gets taken away from you because there are all of these other threads which ask for the data, and this guy is very far. He only, by the time he gets the data, there's also another request which says, give me away the data, right? So basically, this way, this is not a stochastic scheduler because I can deterministically predict that the faraway thread will be scheduled for a single step at a time. And this is a disaster if you run a log-free algorithm because this guy will starve, right? So the point of this example is that this does not hold if the schedule is not stochastic, right? So you have to still be careful that, I mean, you have to have some confidence that your sort of system does provide you with this type of guarantee, right? Okay. All right. So, so this is the example of new models, for example. All right. So then, so let's do a little recap here and see where we are so far. So basically, the story so far is that we want to understand a bit more about what progress log-free algorithms guarantee in practice. We've introduced this slightly wonky stochastic schedule model, and then we've shown that in theory, assuming this model, log-free becomes weight-free. All right, so great. Now, the next question I want to ask is, I mean, actually going towards your question, in fact, can we actually get reasonable bounds for certain types of algorithms under these types of assumptions, maybe making a bit stronger assumptions on how the scheduler looks like. So, I mean, the thing is, if you remember the previous graph here, I mean, what this theorem says is that this will look like this, but technically, like the tail of the distribution could be extremely large. Basically, I'm just telling you that 3 weeks from now, something will succeed, right? Can we get something that approximates this behavior under some reasonable assumptions on the scheduler? So this is what we're going to look at next. Okay? So for this, we're going to assume a uniform stochastic scheduler. So basically, we're going to make sort of a very strong assumption on the order in which threads are scheduled. So basically, we're going to assume that at any point in time, any thread will be like just the scheduler flips a random coin and schedules the next guy as the next step. So as we've seen, this is a reasonable approximation on the average behavior of the scheduler, even though it might not be a very accurate one locally, right? So I want to say we will not claim that the scheduler is uniform generally. It is not. However, we can use this as a lower bound on its long-run behavior. And in fact, we're going to see towards the end of this part of the discussion that this is, in fact, in some sense, we're making a worst-case assumption on the stochastic scheduler. So in some sense, so actually, this is the worst stochastic scheduler you could assume for at least for a large class of algorithms. Okay. So before, if that didn't make entire sense, I hope that I will be able to clarify that. So basically, what we're going to look at is algorithms which follow this pattern. So there's some preamble, some memory allocation, whatever, and then they enter this do-while loop where essentially they try to read a couple of they do some local work, they read some variables, and then they try to make sure that no one has sort of messed up the data structure while they were working, and then sort of they're going to do this via compare and swap or multi-compare and swap or via some transactional thing, and with some probability they will sometimes they will succeed, otherwise they will just restart this loop. Okay, so we've seen the counter which has this, and you can make some map some other data structures on this. What's interesting is that you can actually express the universal construction in a log-free way using this pattern. So practically this pattern is universal, even though it might not be the most efficient way to implement things for certain data structures. Okay? So we're going to care about two specific quantities. The first is the average number of steps that a process needs to take until completing a method call, which is step complexity. And the other one is what's the average number of steps that the system will take until completing a method call. So basically this is basically system latency. Basically this is this bound B that we've been talking about so far, and in fact, this has a very real meaning. It's the inverse of throughput. Basically, if you take 1 over this is number of operations you'll be doing per second. Okay? So again, I mean, just because, so the characterization that I'm going to talk about works generally for algorithms which fit this pattern. However, this is, I mean, there's only so much pain I want to sort of subject it to, so I'm going to assume the special case of the counter here. So remember that the counter has this very, I mean, it's a very, very simple instance of this pattern where you do a read, you do some local computation, then you try to do a compare and swap, right? So you have this very simple automaton which threads are continually trying to go over in order to finish an operation, okay? So is it clear how this piece of code maps onto this sort of Markov chain-like thingy, right, or automaton, if you will? Okay, so what will happen under scheduling, right? So let's say we take the example schedule 1221. These threads are only accessing a single random variable, right? So basically this is R. The scheduler will just schedule them uniformly at random on to take steps on this variable, whether it's read or write, right? So, all right, so at least this is the assumption that we're going to make. So basically imagine that both of them start in a clean state. They haven't read anything. 1, 2, 2, 1. What happened here, at this step, one of them was bound to fail. This guy was chosen to be scheduled. This guy failed, so on its next step, it will have to go back and redo the read, right? So you get this kind of funky automaton game in some sense. Like you have all of these automata, they're coupled by the fact that they sort of work on the same shared variable. And basically, the unfortunate thing is that I could fail because of someone else just being scheduled. So basically, we are sort of, our state is sort of constrained by what's going on at other parts in the system as well. Okay? So does this representation make sense? I just want to make sure, because otherwise the next few slides are going to be quite boring if this doesn't make sense. All right, so the question is, assuming a uniform stochastic scheduler and then threads, what is the average step complexity? So basically, with this game, how often do we actually, does some guy win here, okay? And I don't want to do this for 2 because this is sort of trivial. I'm going to do it for n, right? So basically, imagine I have the scheduler. It comes up with a random string, which is the schedule. So basically, this guy gets scheduled, this guy gets scheduled, this guy gets scheduled. How often does someone succeed, right? So that's the question here, okay? So just imagine. All right, so in every step, we just move one of these small automata chosen randomly. What's the is how many steps in expectation before one element is chosen twice. Right? So basically, one guy has to be scheduled twice to do the read and the compare and swap before anyone else gets scheduled to do the compare and swap. Okay? All right. So, any ideas? Sorry? No. Sorry? Even less. All right. So let's solve a completely different problem. Well, not completely different, but still. So imagine, so there are 365 days in a year. Okay? There are, what, 30-something people in this room. What's the probability that two people in this room share a birthday? They have the birthday on the same day. Has any of you seen this problem before? Okay. So what is the value of k for which we could get really good probability that two people share a birthday? Square root of n. All right. So that's also the answer to the previous question. But let's actually work it out for people who maybe forgot about this problem. Okay. So okay. So basically, we have n sort of days or bins or something, and we're throwing basically balls uniformly at random into some of the bins. We want to know how many balls do we throw into uniformly until one bin contains 2 balls. Okay, so that's pretty much n days, k people. We just sort of bring people in until the first time 2 people share a birthday, right? Did I go too fast on that? So just imagine the room is empty. We bring in someone new until that someone collides with someone else. So basically, they have the same birthday as someone else in the room. Okay, so that's basically equivalent to at least this question. Right? And then we can discuss how it is equivalent to the question we asked before. Okay? So but let's basically express the probability that up to step k, we don't have any birthday collision. Okay? So clearly the first guy in the room will not have a collision with anyone else because there's no one else. The second guy can't collide with the first guy. Third guy cannot collide with the second and third. Like case girl should not collide with anyone else. So this is the probability that we don't have a collision up to step k. Okay? All right. So this is the quantity that we want to approximate, right? So now I will remind you of this classical bit of business which is called Taylor's formula, which says that e to the x is almost equal to 1 plus x for x small, like if we expand the Taylor expansion close to 0. So basically, for x small, this approximation holds. This is useful here because we'll be able to approximate this and this and this as an exponential, right? Since they have a product, they'll multiply it out. Their sort of the exponents will sum up, right? So this becomes very useful because now we can approximate the probability of no birthday collision as e to the minus k times k minus 1 over 2n. Okay? So now it becomes pretty obvious that if I set k to be, let's say, 2 times square root of n, then this becomes a constant, right? So basically, what does this mean? Every time I bring someone new in the room, the probability that he doesn't share a birthday with someone who's already in the room is, let's say, 1/2, right? So how many people can I bring in before certainly there has to be a collision? Well, about, I guess about like 2 or like on average 2, but it could be as high as 10 or something like that, okay? So basically, the sort of moral of the story is that after k equals roughly square root of n, we are pretty certain to have, or constant times square root of n, we're pretty certain to have 2 people sharing a birthday. Okay? Is this fine? All right? Okay. So there are 2 morals to the story. 1, 2 people in this room share a birthday. So please use the coffee break to work out who and who else. Okay? Then the second one is, and this is what I'll discuss in more detail than the previous one, is after square root of n steps are scheduled, some thread will win. Okay? So let's go back to the previous game. So what were we doing here? We're basically like picking random automata and scheduling them for one step. We know that if one guy gets scheduled twice before sort of any other guy gets scheduled twice, that guy will win. So we want to know how many steps do we globally schedule until the first automaton gets scheduled twice. So it's the same problem, right? The steps are the people who come into the room. The automata are the days, right? Are the days of the year. Okay. Does this connection make sense? All right. So basically, what we have obtained is that after square root event steps have been scheduled, some guy succeeds. All right. Any questions? All right. Cool. So what happens so notice that we have assumed a sort of a clean initial condition, right? So we haven't assumed that we stop it at an arbitrary point in time. We sort of assumed like that everyone starts at the read, right? So that we've made that simplification. So what happens in an execution? Here we go a bit back towards the algorithm. So we have all of these read steps, and then at some point, some guy gets scheduled for the second time, okay? Notice that after this guy, there could be like a lot of other guys get scheduled for the second time, but these guys are the unlucky losers, right? Their steps are useless because, I mean, not only they are useless, we're going to see later that they're like pretty bad. Okay, so basically, notice that the threads which actually manage to like escape this. So basically, they don't do the compare and swap, but they just do the read. Somehow escape this. So these steps are not useless, whereas the failed compare and swaps are practically useless for the system. Okay. So again, the moral of the story is that after square root event steps are scheduled, some thread will win. Okay. And that threads compare and swap will actually cause pretty much everyone else who got scheduled to take a read so far to fail. Okay? Does that make sense? So basically, we know that, I mean, the good thing is that some guy wins after square root event steps. The bad thing is all of the other guys who got scheduled up to that point will lose. So practically, we're basically our step complexity is square root of n, great. So our system bound is square root of n, great. So we do get something done every square root of n steps. However, we also waste square root of n steps pretty much for every win, right? So that's pretty bad, right? So basically, the average system latency of the system is order square root of n, and in fact, this is tight. So basically, it doesn't work any faster than this. And then by symmetry, actually, the average step complexity for a counter operation will be order square root of n. Okay. So there's a warning I want to make here, which is that what I presented is not formally correct. So basically, we assumed a uniform initial configuration. In general, this problem does not map cleanly to the birthday problem. You actually have to like work it out and so on. So it can get a bit messy. The other thing which we haven't modeled and sort of which you should really think about is that technically it's not enough for a guy to take 2 steps in a row to win. Actually, imagine that the second process here got scheduled, so he's succeeding now. This guy, in order to succeed, he will actually have to take 3 steps. He had to do the failed cast, a read, and then another cast, right? So does that make sense? Let me do it again. So basically, both of them were reading. This guy gets scheduled. Basically, this guy has to get scheduled once for the failed cast, and then 2 other times in order to succeed after this point, right? So our analysis here is very, very flaky. So what I gave you is just kind of an intuition for why square root of n is the right thing. But in fact, square root of n is the tight version here. There's a whole paper proving this. So I mean, this is not the easiest thing to prove. Okay. We also have argued that latency is the same as step complexity just by symmetry because all of these threads are sort of symmetric. They get scheduled together. However, formally, you have to do this by Markov chain theoretic techniques. So, I mean, this is not to scare you, just to sort of say there are ways to get around these problems and make an intuitive argument correct. It's just that you need to think about them a bit. Okay. So what is the full result saying? So basically, the full result says that under a uniform stochastic scheduler, we're going to have step complexity, which is order of the preamble plus square root of n times the size of the loop. So basically, one thread will have to do the loop about square root of n times in order to succeed. And the system latency is pretty much the same by symmetry. Okay? So what does this mean? Okay? I mean, morally, this just says that under high contention, this loop will have to be tried square root of n times by any arbitrary process in order to succeed. Right? So basically, square root of n repeats are the price of contention under this model. Okay? So a thread win will cause about square root of n others to fail their validation. So, I mean, again, you have to sort of play optimistic versus pessimistic here. So basically, in the worst case analysis told us that log-free algorithms starve threads. So the worst case was unbounded. First, we got this to something like 3 weeks, right? This was what the first result told us. That there is a bound, just that the bound could be very large. Then we made another assumption on the scheduler, and we got the fact that basically it's square root of n, right? Unfortunately, this is as far as we go. So technically, this is tight. So you can't really improve it. This is what it is. Okay. The other thing which is kind of interesting is that under the scheduling model, the algorithms are fair. So whatever the system does, like however many steps the system does on average to succeed, that's what the average number of steps that a thread will have to do on average to succeed, right? So this is, I mean, basically this says that processes will complete operations at the same rate as the system, which is not entirely surprising because everything is symmetric, okay? So here are a couple of extra questions to think about. Okay, so one thing is, what happens if the probability distribution is not uniform? Okay, so imagine that I have some preference, some bias towards one of the threads. One thread gets scheduled with probability, I don't know, half, and all of the other threads share the other 1/2 probability. So then the question is, what happens in that case? Okay. So another way to, I mean, just to go back to the birthday problem version of this. I mean, in practice, birthday probabilities are not uniform. Basically, there are certain dates around which more babies are born than other dates, right? So then the question is, how does this affect this square root of n number? Any intuition there? Sorry? Yes. Yeah, obviously. Yes. So the obvious observation is that like if you have higher probability around certain dates, the probability that you're going to, I mean, the number of guys you're going to have to get into the room before a collision will decrease, right? But the exact number for this is sort of very interesting. So I challenge you to think about what the exact sort of value is with respect to some arbitrary probability distribution. Okay. Now imagine we want to have a thread do 3 steps before succeeding, right? So basically, somehow the algorithm now is you have to do 3 steps in a row before succeeding. If someone else succeeds before you do you're done with your three steps. You just get reset to 0 and you have to try again. Okay. So then, again, I'm going to resort to you. So then, what does that square root of n number increase or decrease? If you need to do square root of n steps in a row. If you need to do 3 steps in a row. Yeah? It will increase, obviously. Yeah. Any ideas as to what it will be? All right. So it's n to the 2/3, in fact. And I mean, so the final challenge is, what happens if you need to take k steps and succeed with an arbitrary distribution? Okay. So I claim that there is a very short answer to this. Okay. So you can probably work this out in half an hour or something. Okay. So these are just questions I'm going to leave out there. If you have, I think this is not on the exercise sheet. So if you have questions, answers, or clarifications, you can just send me email and ask. Otherwise, if you're just curious about the result, there's this paper in PodC 15 which does this for pretty much any it does it for any distribution and any of these contention games that you might be interested in. Okay, so this is yeah. So this is what it is. Okay, all right. So the story so far is that our goal was to look at how log-free algorithms do in practice. We've seen that log-free algorithms are almost weight-free in theory under some scheduling assumptions. We got some performance upper bounds. Okay, there's this last piece of the puzzle which I want to really briefly go through, which is, okay, so we saw that because there's contention, there's a thread will have to try multiple times to go through the this kind of read, compare, and swap loop in order to succeed, right? There's some kind of non-trivial probability that you're going to get interrupted, and you're going to have to try a lot of times in order to succeed. In fact, that number was, we computed it for a specific distribution, and it was square root of n. Okay? So this is the story so far. But then there are all of these effects which we haven't modeled so far. So for instance, how much do we lose in practice because of contention? So we're running this on a real system, so it's not really clear basically what the extra costs because of cache invalidations and so on are. But there is a sort of a simple way to do that, which and we're going to do that by hardware simulation. And this is the part which is really research. So I'm actually I'm just going to go through it a bit faster, right? So this is sort of just an interesting data point. What happens if a thread would not get interrupted between its read and its compare and swap, right? What are the other overheads amounting to? Okay. So the motivating question here is, all right. So we've seen how this Michael-Scott queue used for packet processing looked like in practice. Okay. So the thing that really bothers me about this graph is that it's somehow not very intuitive. At least for a theorist, it's not very intuitive why this looks like this. So I always thought that when you ran a queue, there's like this sort of, obviously its throughput cannot be linear with the number of threads because there's kind of a contention point. But my intuition was always that there's kind of this sort of saturation point, and then this data structure would gracefully tend towards the saturation point and then stay there somehow. There's like an upper bound, upper limit on the number of packets you can process per second, and you gradually reach that bound. Okay, so then the question is, that's kind of saturated throughput, right? But in practice, you see this huge gap, and in fact, performance sometimes gets worse as you increase the number of threads, right? So this is not something that actually theory can explain very well because it has to deal with how the cache coherence system works, right? So where is this difference coming from? And this is the question that we started from here. And part of this difference is coming from, this is just the counter, the example of the counter just mapped out on the queue. So basically, on a log-free queue, you're going to read the head. You're going to look at the next node. If you want a dequeue, you're just going to try to swap this pointer from here to here. Okay? So basically, we know that in a contended execution, two threads will try to do this at the same time. One of them will have to lose if they're basically both at the point where they've read the head. So technically, we're going to get, because of contention, one of the threads will have, a thread will fail. And in fact, the theory we just saw basically said that under high contention, one in square root of n accesses will succeed. So this is just mapping out the simple example we did before, but on a slightly more complicated data structure. This is on the Michael-Scott queue. Okay. So then the question is here, what happens actually at the hardware level which makes things go from this nice theoretical saturated throughput point to this sort of sad little point that we see in practice, okay? So let's look at, there's kind of a, here's a simplified explanation to what happens here. So basically, imagine that there are two cores which are trying to do this read and compare and swap sequence here, okay? Now, in a cache coherence system, basically this read will map into a request to the directory-based cache coherence protocol, which is basically this thing living on the chip for Intel and AMD systems, where basically this is basically saying, I want the cache line corresponding to this variable R, either in shared or exclusive mode, depending on how the prefetcher does things for you. Okay, so basically, let's assume that this is exclusive state here, just to simplify the example. Okay, so basically, the read maps to a cache coherence request. It gets to the directory-based cache coherence protocol. This thing, it can be enormously complicated, so we don't really care what it will do, but eventually it will reply. So we know that all implementations guarantee that eventually, after something happens, you will eventually get the data in exclusive state. Okay? Then this is sort of money time. So now you need to perform all of these steps and do the compare and swap as soon as possible because there are all of these other threads who want to do exactly the same thing. So in particular, because if it's contended, you're very likely to be interrupted here. So basically, there's another request, goes to directory-based cache coherence protocol. That guy says, sorry, you have to give up the data. So basically, there's this invalidation request saying, give up the data immediately. And in fact, because cache coherence protocols are all about making progress, you only get to perform one step by the time you've gotten this request. After this, you have to give it up. I think this is constant throughout all of the coherence protocols that I've seen. Okay, so you have to immediately give it up. And it eventually gets to this guy. Say this guy succeeds, even though in practice this guy could get interrupted as well, and that guy can get interrupted as well, and they usually get these long chains. So basically, you sort of get a failure here. What's really sad is that you wasted a lot of time. I mean, practically this whole thing, this whole sequence here was wasted because you did all of this messaging for nothing. You didn't actually get any useful work done. Okay. So did this example make sense so far? All right. Okay. So we waste a lot of time because ownership of the variable circulates without useful work. The difference between what we think the data structure might get and what you see in practice comes largely because of this extra overhead, which is very hard to model because it's kind of system specific. Like these latencies can be different, and the protocol can be slightly different, and so on. However, so in practice, what the execution does is basically there's a CAS attempt, there are a couple of ownership transfers, there are failed CAS attempts, another basically ownership transfer, and so on and so forth. And only a part of these, basically the ones that result in successful CAS attempts are actually useful. There's a lot of just data traveling around without any work getting done, okay? So in order to see how expensive this part is, we're actually going to add a new instruction to the hardware which allows the thread to say, all right, so when I get this piece of data, let's say the cache line corresponding to memory location R, I'm not going to reply to coherence requests for a short amount of time. Basically, this is kind of this is an estimate on the amount of time I need to perform my read, compare, and swap sequence. Okay? Does this make sense? So we're going to say, sorry, once I get this cache line for 50 cycles, I won't be reachable. I'm just setting my phone on silent. Okay? So let's see. So basically, the idea is that we want to make as many cache line transfers useful as possible. Okay? So how does this map onto our example? Now instead of a regular request, we're going to have a lease request, which has this extra time parameter, and which actually the directory cache coherence protocol doesn't really care about, but I'm just modeling it here. It will eventually get a response. It starts a lease interval during which I will just delay probes coming to my core. So basically, this guy comes in, he wants to do either a regular request or a lease request, it doesn't really matter. I'm just going to delay this either until I complete my compare and swap or until the interval ends. Okay? Does this make sense? It is just sort of just a simple trick. Okay? I want to know how much would I gain if I had this extra operation in the hardware. Okay? So in this case, I would succeed. Everything is great. This guy can do its own thing, and so on and so forth. Right? So the idea is again we just want to make cache transfers more more valuable. Okay. I mean, there's also a bad case here. So it's not something for nothing. So the bad case is when I do the same thing. I do the read request. I start my interval, but my interval is too short. Okay. So in this case, I've delayed this guy here, but my interval runs to completion here. So I have to give up the data because otherwise the system would just block on me, right? So this interval has to be bounded, and in fact, in practice, has to be pretty short. Okay? So in this case, I mean, I've actually slowed the system down by this extra interval during which I actually delayed things, but I didn't get any payoff out of it. Okay? So this is sort of the bad case. And we're going to wager that the bad case happens less often than the good case. In fact, the performance of this will hinge on how good we are at guessing the length of the interval. Okay? So more precisely, this is a project, a pretty fun project we did a couple of years ago, where essentially we added these are sort of the C calls, but we actually added like hardware instruction to this. And obviously there's this performance penalty, which I'd like to emphasize, but usually this, if you pick a reasonable value for the interval size, you can get it to happen within 5% of the time. All of this logic can be implemented by cache controllers, and the max lease time can be in the order of 1,000 cycles, even though much less is also okay. So then we implemented this in a hardware simulator. So basically, there's this huge piece of software which allows you to add instructions. Some of them will get treated by the hardware. Basically, they just get mapped by basically the pin tool to the hardware instructions. The other ones will get mapped to your software code, which allows you to simulate stuff. Okay. So basically, here's and sort of here heading towards the end here. I just want to tell you what you get with this, right? So basically, this is what happens with the lock-free queue if you add this kind of lease. Instead of doing a regular read, do a lease read. And then instead of doing a compare and swap or a write, you do a release. Okay? So you just add this, you just modified the read, compare, and swap thing with basically lease and read, compare and swap, and release. Okay? So this is the throughput as before, and this is what you get via these leases. Okay, so the improvement here is pretty significant, but actually the thing that sort of I find more interesting is that you get close to this kind of ideal behavior which you would expect from a queue, right? So basically, yeah. So for these examples, we tuned it. So we just fixed it to be like 1,000 or something. There's actually an algorithm for doing that. So there's like an algorithm which kind of learns the time for various pieces of code. Okay. All right. So the other thing which I want to show you is that basically why this is. I mean, why you get an improvement in performance. And it is because of less messaging going around. So basically, we looked at the energy which is spent per operation as you increase the number of threads. So basically, you see that the lease version, which is in green here, has this kind of linear behavior, whereas the no lease version has this exponential behavior. So it just tells you that there's just exponentially less messaging going around, which is why you're getting an improvement in performance. Okay? So I guess the point of this part of the class is just to give you an idea of how much extra overhead the hardware adds in case of contention. And the point, it's not to really sell my chips with this lease instruction because I don't have them, but it really is that you have to understand that contention really is a killer in certain cases. So it can be the difference between something like this and something like this. So there are other ways to deal with contention, like backoffs and so on. But the main reason why we did this hardware simulation thing was to be able to sort of tell you what's the best thing you could get within reasonable algorithms. Okay. So with this, I think I'll stop here, and yeah, I'll take questions here. All right. So, okay. So I think there are a couple of questions there, if I can deconstruct them. So first, you want to know how our benchmark works. First, our benchmark works by inserting like 100,000 elements, and then every thread does insert and delete for a certain period of time. Okay, so this is a completely synthetic benchmark. Okay, we actually have other benchmarks which do like we do a real application on top of actually a similar object. So I can show you those in the break if you want. So this is just a synthetic experiment where you just do insert remove because we want to stress the queue as much as possible. Okay, then the implementation of messy that we use is I think pretty standard. In fact, it's the standard version that comes with Graphite, which is this kind of multiprocessor simulation software. Okay, so as far as I can tell, I mean, we didn't see any specific jump in performance or change in the behavior because we were stressing the cache coherence protocol. In fact, as far as I know, the Graphite is sort of cycle accurate, so it's tested against real processors. So I think you would get similar results on a real processor if you had this extra instruction. Okay, so I guess the answer to the second question, your second question, which is there any weird behavior that messy gets because of this? I mean, it gets weird because the performance is pretty bad, but I don't think there's a bug in it or anything like that. Okay. Yeah. Yes. In fact, because it's gonna queue like all of the requests are gonna queue at the directory, right? Basically, like there's this shared. Yeah. I mean, it does. Queuing times are reasonably high, yes, but it does sort of. I mean, that's what you get in practice as well, right? Yeah. 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 Okay, so I can show you how this changes if you add some payload to the node. So basically, every time you remove a node, you actually do something so that there's less pressure on the queue. Right here, we really wanted to know what happens under contention, but it doesn't get much better. I have to tell you. Basically, what happens if you add some sort of backoff here is that this will sort of flatline, so it's not as bad, but it sort of still ends up here. Okay. Yeah, exactly. Yeah. So you don't lose, you don't get below the 8-thread mark, but it's not much better than the 8-thread mark. Right? All right, sure. Yeah. So this is 64. I mean, this is up to 64. So these are 64 threads and 64 cores. Okay. Yep. Yeah. 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 So I mean, I think the closest thing that we tried related to this was backoffs. So we implemented backoffs, and then you do get a bit of an improvement in the sense that it doesn't your throughput decreases or does not decrease or decreases less, but performance is still not good. I mean, the difference between the best backoff we could find and this line is really like significant. Yeah. Yes, but then there are overheads to combining as well, right? There's has to be this thread who combines and so on. So I'm not sure what the answer, like what the precise answer there is. Yeah. Any other question? Yeah. 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 Yeah, I mean, in short, yes. The longer answer is basically that theorem, if your queue is randomized, then that theorem does not, I mean, basically that lower bound becomes log n, is not linear, but it's like exponentially lower. But as far as I know, there are no randomized queues which actually get to like log n or something. So yes, it's definitely an interesting design space. And we're going to see examples of that in the next part of the lecture. But I think this is largely open. So, for instance, I don't know of any queue which gets to log n. Even more than that, I don't know of any practical algorithm which gets significantly beyond this bottleneck without any relaxation. Okay. Any other question? Yeah. All right. Thanks.